welcome back. This video is a brief overview of everything that you need to know for topic 2, atomic structure, for the upcoming IB papers. So of course you need to remember atoms are made of 3 subatomic particles: protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. Electrons are found outside of the nucleus. You do need to know how to read the basic structure of an element on the periodic table. So A is the mass number, Z is the atomic number, and X, of course, is just the symbol of the element. So the atomic number is equal to the number of protons. And for a neutral element, that will also be the same as the number of electrons. The mass number is equal to the number of protons plus the number of neutrons in the nucleus. So you should be able to look at an example and decide how many protons, neutrons, and electrons there are. So just as a quick example, if we had something like Al 27 and 13, you should be able to identify the number of all of the subatomic particles there. So the number of protons would be 13, electrons would also be 13 because it's neutral, there's no charge here. And the number of neutrons would be 27 minus 13, so 14 neutrons in that sample. And again, the number of neutrons we can find by looking at the mass number. The mass number is equal to the number of protons plus the number of neutrons. So if we know the number of protons, we can subtract that from the mass number to give us the number of neutrons. Not all atoms of an element will have the same mass. Isotopes are atoms of a given element that have different numbers of neutrons. So atoms of the same element with different number of neutrons. So just as an example, we could have something like chlorine 35 and chlorine 37. Those are isotopes because the mass number is different. Remember, the number at the top is the mass number. So these two would have different numbers of neutrons. And we can easily work out the average mass. So if I told you that chlorine 35 was abundant in nature 77.5% of the time, and chlorine 37 was only found 22.5% of the time, we can find the average mass of this element. So average mass that you see on the periodic table is a weighted average of all of the isotopes. It's a weighted average of all isotopes found in nature. So if chlorine 35 is found 77.5% of the time and chlorine 37 is found 22.5% of the time, we can find the average mass. So we're going to take, average mass, we will take the total mass over the number of atoms in our sample. And if we're working with percentage, we can assume that the number of atoms is 100 because our percentage should add up to 100%. So to find the total mass, you take your mass, so for chlorine 35, the mass is 35, times the percentage plus 22.5 times 37 gives us a total mass of 35.45. So then we just divide that by 100 to get 35.45. And you can check on the periodic table, that is the average mass of chlorine. Not only do we have isotopes, but we also have ions. Ions are atoms of the same element with different number of electrons. There are two different kinds of ions. There are cations and anions. Cations are positive charge. There's less electrons than normal. Anions have a negative charge and there's more electrons than normal. So just as a brief review in case you forgot, protons of course have a positive charge. Neutrons are neutral, they have no charge. And electrons have a negative charge. So let's look at an example of an ion. So protons, that number hasn't changed, it's still the atomic number. The atomic number of an element will never change because if you change the atomic number, you change the element itself. So the number of protons for a given atom should always be the same. So protons, that hasn't changed. Neutrons, we take 27 minus 13, and that is still 14. But electrons, notice we have a +3 charge, and a cation means that we have less electrons than normal. So I'm going to take 13 minus 3, and I have 10 electrons. So that means that this aluminum has lost 3 electrons. That's why I do 13 minus 3. So basically you just do the opposite of whatever the charge is. Let's try a negative real quick. Let's say that we have oxygen 2 minus. The number of protons is 8. That's the number down at the bottom, the atomic number. Neutrons are 16 minus 8, which is also 8. And electrons, we have 8 plus 2, because the negative means that we've gained electrons. There's more electrons than normal. So here we also have 10 electrons, 8 plus 2. You should also be able to determine the atomic mass given a mass spectrum. And that is a graph that shows you the percent abundance and the mass. It's the exact same as what we just did for chlorine. You would just be using graphical data. And I can put an example of how to do that up on my channel. A big part of chapter 12, of course, are electron configurations. And electron configurations are actually pretty fun to write out once you get the hang of it. One key part of electron configurations that we need to understand before we can move on is that the energy of an atom is quantized. And that basically just means that energy is divided into steps. So quantization is basically like a stair step. Electrons in an atom can be on different stair steps within the atom, but they have to be on a certain stair step. If you're going up the stairs, you can't hover in between two stair steps. That's not possible. You have to be standing on one step or moving up step by step. You can jump 2 steps, sure, but you cannot be in the middle of a step. And it's the same with electrons in an atom. Electrons have a specific amount of energy, and it's actually divided into levels. And how we found this to be true is by looking at the atomic emission spectrum. And the atomic emission spectrum is proof that energy inside of an atom is quantized. Basically what happens in an atomic emission spectrum is electrons are hit with energy, they become excited and full of energy, but when they relax, they emit light. And what's interesting about this light is that it is discontinuous. The atomic emission spectrum is discontinuous, which means that it produces specific wavelengths of light, which shows that a specific amount of energy is released. If we were to look at a prism, remember from like middle school science, if you shine light on a prism, an entire rainbow, the whole visible spectrum would be visible. We could see the whole visible spectrum, and that is continuous light. continuous. So if electrons were not quantized, when this whole process happens, the light should have been continuous. However, because specific wavelengths of light are shown when an electron becomes excited and then releases energy, that proves that energy in atoms is quantized. Those electrons are emitting specific wavelengths of light, which corresponds to a specific amount of energy. So that is just a brief overview of the atomic emission spectrum. I can put more information on my channel as well. So we know that electrons are quantized. They are in specific energy levels, and those are known as atomic orbitals. Atomic orbitals. That is where we would have a 90% chance of finding an electron. And orbitals will have different shapes. There are 4 different orbitals, S, P, D, and F. You only need to know the shapes of S and P. S is a sphere, and P we call like a dumbbell shape, and this would be along the y-axis. There would be one on the x-axis, and on the z-axis coming outwards towards us. D kind of looks like a flower. F, we're still unsure what it looks like, but you actually don't need to know those shapes. You do, however, need to know how many electrons can fit into each of these sublevels. So in sublevel S, we can have a max of 2 electrons. In P, we can have a max of 6. D holds 10, and F holds 14. So S, P, D, and F are the shapes of our orbitals as well as sublevels. So the levels of energy that an electron can be in are 1 through 7, and they correspond to the periods or rows on the periodic table, which is really handy. So we can have energy levels 1 through 7, and whichever energy level you are in, that corresponds to the number of sublevels in that energy level. So for energy level 1, we only have 1 sublevel, 1s. For energy level 2, we have 2 sublevels, 2s and 2p. For energy level 3, we have 3 sublevels, 3s, 3p, and 3d. For energy level 4, we have 4 sublevels, 4s, 4p, 4d, and 4f, and so on and so forth. So for electron configuration, all that we're looking at is how electrons are organized inside the atom. How are the electrons arranged in their specific energy levels? And there's a few rules that we can follow that makes electron configurations and orbital diagrams very easy to write out. So the first part of electron configurations is the off-bow principle. And the off-bow principle just says that electrons are placed in the lowest energy level first. So we just need to know the order of energy levels. We need to know which energy level has the lowest amount of energy. And there's a really easy trick to do this. Hopefully your teacher showed you this. All that we're going to do is draw diagonal lines moving upwards. So first we would fill 1s, then we would fill 2s, then we would fill 2p, and then 3s, and so on and so forth. And this is a really easy tool. You can draw this on any scratch paper that you have during your exam. As long as you know how to write out your numbers and draw your diagonal lines, you should always be able to write out your electron configuration in the correct order. So for electron configurations, which again is just how electrons are arranged in the atom, you need to know this rule, and you just need to know how many electrons can fit into each sublevel. With orbital diagramming, it's the same thing as electron configuration, except we're using arrows to represent electrons, and there are 2 more rules that you need to know for that. The Pauli exclusion principle, which just says that two electrons in the same orbital have to have opposite spins, and I'll show you an example in just a second. And the last thing is Hund's rule. Every orbital in a sublevel needs at least one electron before any are paired. Any are paired. And I will show you an example of that as well in just a second. So let's look at an example of an orbital diagram. So let's look at aluminum that we had before, 27, 13. This is just a neutral aluminum atom. There's no charge there. We know that there's 13 electrons. So let's see if we can draw out the orbital diagram. So we need to know which order our sublevels need to be in, as well as how many we need because we have 13 electrons. So remember we said before, the S orbital can hold 2 electrons, P can hold 6, D can hold 10, F can hold 14, and I need to follow this structure here. So the orbital diagram shows the number of electrons in each sublevel, and we use arrows to symbolize electrons. So 1s would have 2 electrons, and according to Pauli exclusion principle, they have to have opposite spin. So I put 1 arrow up and 1 arrow down. I've only placed 2 electrons. I need 11 more, so I'm gonna do 2s, 1 arrow up, 1 arrow down. Next, we move on to 2p. And this is where Hund's rule is important. I'm going to put 1 electron in each orbital before pairing any off. So I have 1, 2, 3, 4, 5, 6, 7 electrons, 8, 9, 10. Let's see what comes after 2p. Following my diagonal line, I need to go up to 3s. So 3s, 1, 2. So now I have 12 electrons. I need 3p, which only has 1 electron in it. So let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's all that you need to do for orbital diagramming. You're just putting in your electrons as arrows. You're filling a whole sublevel first before pairing off any electrons. And you're just following the off-bow principle, putting all of your numbers in order. So not super difficult. Electron configuration is almost the same thing. We're just not using the arrows. So electron configuration is somewhat easier. So let's draw out the electron configuration. We have 1s2, 2s2, 2p6, 3s2, 3p1. So we took the number of arrows in each sublevel and used it as an exponent, and that is an electron configuration. We can use the electron configuration to find an important type of electron called a valence electron. Valence electrons are electrons in the highest energy level, and they are responsible for bonding. So it is really important to know how many valence electrons each atom has. And let's look at aluminum. The highest energy level I have is 3, and we're looking at energy level, not sublevel. So I have 3s and 3p. The total number of electrons I have in energy level 3 is 3. So aluminum would have 3 valence electrons. You also need to know how to write out the electron configuration of an ion. So if we looked at aluminum 3+, remember that the electrons are equal to 13 minus 3, or 10. So for aluminum 3+, I would write out the electron configuration as 1s2, 2s2, 2p6, and that is it for aluminum 3+. The periodic table is actually set up in such a way that it really helps you with electron configurations. So the blocks are groups 1 and 2 are the S block, groups 3 through 12 are the D block, groups 13 through 18 are the P block, and down at the bottom the lanthanides and actinides are the F block. So really briefly, I'm just going to label my rows, my periods. So 1, 2, 3, 4, 5, 6, 7. And of course, this is not perfect by any means. So let's look at where aluminum would be on the periodic table. And again, this is just a rough drawing, but the different blocks tell me what my electron configuration should end with. So in group 1, we would have S1. In group 2, we should have S2. Moving over to the P block, group 13 would be P1, 14 would be P2, 15 would be P3. So look at where aluminum is. And again, my drawing is not perfect, but you can look on an actual periodic table. Aluminum is in group 13, row number 3. So aluminum, again, it's in row or period 3, group 13. Looking at which block it's in, I should know that my electron configuration should end in 3p1 because these numbers refer to the energy level of the highest electrons, and then the block tells me which sublevel, and the group will tell me how many electrons are in that sublevel. So starting with group 13, again, that's P1, and so forth all the way until group 18 is P6. So if we looked at something like hydrogen, which is up here in the corner, I know just using the periodic table, my electron configuration is 1s1. And you can do this for any element on the periodic table. It's just a quick way to find your electron configuration. Super easy. And I'll put a more detailed video of how to use this system on my channel. Just one last thing, if you see the term ground state electron configuration, that just means the electrons are in the lowest energy level possible. That's just a normal electron configuration. So that's just a normal electron configuration. So again, this was just a brief overview of everything you need to know for topic 2. I can put more detailed examples on my channel. I do hope this was helpful. If there's something that stuck out to you that you do not remember, take the time and study that before your exam comes up. Thank you so much for visiting my channel.